All right, everyone, let's dive right in. Today, we're exploring the hidden world of ionic equilibrium. And trust me, this isn't some obscure lab concept. It's an incredible, invisible ballet happening in every drop of water, from your morning coffee to the very cells keeping you alive. So, have you ever really stopped to wonder about something as simple as this? Why do these everyday things taste so incredibly different? The answer isn't just flavor, it's chemistry. It's all about that invisible ballet of charged particles. And by the end of this, you're going to see exactly how it all works. To really get a handle on this dance, we've got to meet the dancers, right? So let's start with the key players in any solution, the ions and the stuff that makes them. Okay, so our main characters are these things called electrolytes. When you dissolve one in water, it basically shatters into ions. Those are just tiny particles with an electrical charge. And because of those charges, the water can now conduct electricity. Electrolytes are what turn plain old water into a live circuit. Pretty cool, huh? But here's the thing. Not all electrolytes are created equal. You've got strong electrolytes, they're totally committed, they jump in the water, and bam! Every single molecule breaks apart. It's a one-way street. Then you've got the weak electrolytes. They're a bit more indecisive. They only partially break apart, creating this constant back and forth, a two-way street, where molecules become ions and ions snap back together into molecules. And that state of balance, that is the whole shebang. That's ionic equilibrium. It's this sweet spot where the breakup rate and the get back together rate are perfectly matched. And here's the absolute key. This whole equilibrium dance, it only happens with those indecisive weak electrolytes. All right, so we have our ions dancing around. Now let's talk about how they behave. In chemistry, there are two star roles that ions can play, acids and bases. So let's check out the rules of engagement. So the first real crack at defining these guys was the Arrhenius theory. And you know what? It's super straightforward. If a substance releases a hydrogen ion, an H+, in water, we call it an acid. If it releases a hydroxide ion, an OH-, we call it a base. Simple, clean, and a fantastic place to start. But like a lot of first drafts, it had a few holes. For example, take ammonia, NH3. We know for a fact it's a base, but look at it. There's no OH group there for it to release. So what gives? How can it possibly be a base if it doesn't fit the rule? This little puzzle meant chemists needed a better definition. And that brings us to the upgrade, the Bronsted-Lowry theory. And this one is just so much more elegant. It redefines the whole thing as a game of pass the proton. An acid is a proton donor, a base is a proton acceptor. That's it. And just like that, our ammonia problem is solved. It can't donate an OH, but it can absolutely accept a proton from a water molecule. And this brings us to the real MVP of this entire story, water itself. Water is a true chemical chameleon. The fancy word is amphiprotic, but all that means is it can play for both teams. It can act like an acid and donate a proton, or it can act like a base and accept one. This flexibility is what makes it the perfect arena for all this chemistry to happen. Okay, so if water is the arena, we're gonna need a scoreboard, right? We need a way to measure all the action that's happening inside. And that, my friends, is where pH comes into play. Now, get this. Even in a glass of the most perfectly pure water, there's a little bit of action going on. A tiny, tiny fraction of water molecules are constantly splitting into hydrogen and hydroxide ions, and then immediately snapping right back together. It's called self-ionization, and it's like a constant, quiet hum in the background of every aqueous solution. Now, trying to measure those tiny ion concentrations directly would be a huge pain. So scientists came up with a brilliant shortcut, the pH scale. It's a genius way to convert those messy, tiny numbers into a simple, easy-to-read scale, usually from 0 to 14. Think of it as the official scorecard for the world of acids and bases. And the rules are super easy to remember. A pH below 7 means you have an excess of those H+ ions and your solution is acidic. A pH above 7 means you have more OH- ions and it's basic. And a pH of exactly 7, that's the sweet spot. That's perfectly neutral. So we have this delicate balance happening all the time. But what if we want to take control? What if we want to manipulate that balance? Well, as it turns out, both nature and science have some incredibly clever tricks up their sleeves. And to understand the first trick, I want you to think about this analogy. It sounds a little strange, I know, but just stick with me here, because it sets up a really powerful chemical idea. This is what we call the common ion effect. So let's say the few H plus ions from water's natural self-ionization are the dogs. Now imagine you add a strong acid. You've just flooded the solution with a ton of powerful new H plus ions. These are the lions. So what happens to the dogs when the lions show up? They get real quiet. The system basically says, whoa, we have plenty of H plus ions now, and it pushes back, suppressing its own tendency to make more. The balance shifts. Now, this whole principle is the secret behind one of the most important tools in chemistry, a buffer solution. A buffer is a special mixture that does something that feels like magic. You can add a bit of acid to it or a bit of base, and the pH barely moves. It's like a chemical shock absorber. It just resists change. So why should you care about this? Well, here's why. You are alive right this second because of a buffer. Your blood is an incredibly fine-tuned buffer solution that works around the clock to keep its pH locked in right around 7.4. If that number changed even a tiny bit, critical systems would fail. So yeah, buffers are literally a matter of life and death. All right, I've got one last little twist for you. You'd think that dissolving a neutral salt in water wouldn't change the pH, right? I mean, salt is neutral, but not so fast. Sometimes the ions from that salt will actually react with the water itself, a process we call hydrolysis. And when they do, they can actually steal protons from the water or donate them, making a perfectly neutral solution suddenly acidic or basic. It's just one more layer to this incredible, invisible dance. So when you boil it all down, the big takeaway is that this invisible world is constantly in motion, always seeking balance. And if something as simple as dissolving a pinch of salt can fundamentally alter the chemistry of water, it really makes you wonder, doesn't it? What other intricate, invisible ballets are unfolding all around you right now?